Where did all the baryons go? We know almost nothing about the universe. Sure, we've got some things nailed down. We know about the existence of dark matter and dark energy. We know about the Big Bang. We know how galaxies form over the course of billions of years. And most painfully of all, we know that normal matter, the kind of matter that makes stars, galaxies, planets and you, is no more than 5% of all the mass and energy in the universe. And what's worse, we don't really know where half that normal matter is. A census of the universe. First, a quick definition. For the purposes of this conversation, served with a heaping spoonful of human bias, we will call normal the matter that makes up familiar, everyday, household items like TVs and furniture and molecular clouds. Astronomers call this baryonic matter, because it's mostly made of baryons, protons and neutrons and the like. So, even though baryonic matter is nothing but a bit player in the great game, you could wipe away every single galaxy in the universe and the progress of cosmic history would go on unblinking. We're the most familiar with it, so we call it normal. And the very fact that we have a problem counting all the baryons may seem like a bold claim to make. That we know what the universe is made of, even if we can't find it. But we have two giant pieces of evidence that help us count up all the baryons, even when they don't light up for our telescopes. First, and this is amazing for me to even type, we have a pretty firm grasp of the physics of the universe when it was only a dozen minutes old. At that time, billions of years ago, the universe was small, hot, and dense enough for the first protons and neutrons, red baryons, to condense from the primordial soup. And since we understand nuclear physics well enough to make power plants and bombs, we can make predictions. Those predictions tell us how many total baryons ought to exist in the cosmos, along with the ratios of light elements, like helium and lithium, to hydrogen. And since we observe the same ratios that our calculations predict, we have a lot of confidence that those calculations are good enough to put a limit on the baryon population of the universe. Second, we have the cosmic microwave background, a magnificent source of light from when the universe was a mere 380,000 years old. The light was released just as the universe cooled from being a plasma. And once again, we understand plasma physics well enough to compare the light that we see to the light that we predict, and that tells us about the total number of baryons known to inhabit the cosmos. In both cases, the numbers agree. 5% of all the mass and energy in the cosmos. That's all the baryons the universe is going to get. On the hunt for baryons. A bunch of baryons wind up compressing down and igniting nuclear fusion, lighting up as stars. And a bunch of those stars end up collecting together into giant cosmic cities, the galaxies. Over here on Earth, which is also made of baryons, we have a pretty straightforward time counting up all the stars and galaxies in the universe, because they're relatively bright and spotting them is exactly what we make telescopes to do. Beyond that, we have a few other tricks for counting baryons. We can look at light that has passed through billions of light years of scattered gas. The gas itself is too thin to see, but it will absorb some of that background light, allowing us to estimate how many baryons are just hanging out in giant gas clouds. Going even further, we can look for the subtle bending of background light to look for dim, compact objects. Things like black holes or rogue planets, which are also made of baryons but just not very bright. All told, we're able to account for about half the known baryons in the universe, which is a bit of an embarrassing state of affairs. Looking in the cosmic couch cushions. One possible solution to this cosmic quandary is that the baryons are somewhere out there, not lighting up as stars, not compact enough to make gravitational lenses, and not dense enough to absorb background light. The missing baryons could just be floating around, minding their own business, not really associated with any particularly interesting object. And in the larger universe, when you want to get away from the hustle and bustle of the galaxies, you go to the filaments. Long, thin tendrils of gas that connect galaxies to their neighbors, like long stretches of empty highways between cities. We know of the existence of these filaments through computer simulations, but measuring them is much harder, since they're so thin and feeble. But recent techniques are starting to open them up. If the gas in the filaments is hot enough, Then the light from the cosmic microwave background will energize as it passes through, creating a hot spot in our microwave imaging known as the Sunyaev-Zeldovich effect. The effect for each individual filament is super small and almost impossible to measure, but by stacking up hundreds of filaments and superimposing them on top of each other, it's enough to build up a clear signal. And that's what we're beginning to find. About half the baryons in our universe eschew big city living, and prefer to live in the sleepy rural stretches between them. Thanks for watching.